To future clever crackers, remember, tricks are best served yellow, unless, however, it's yellow snow. But what's yellow that's not yellow snow that can be represented as a trick?
I've got it. It's the Morrison's yellow card.
Holy Batman, I think you're right. How did you get that?
Well, Robin, I've tried yellow snow before. Not a good trick.
Damn the Riddler. That reminds me though.
The trick?
The trick. Did you put your card back in the deck this time?
Yes.
Right. So if I've got it right, you cut it here, you put that onto the bottom. Get ready for some magic. You do a little twizzle. You slap your face. You drop them on the floor. And then is this your card?
Yeah. As if by magic.
It's miles better value. So,
now onto estimation. So, in most subjects, estimation sort of not being a melon, but in stats, it's actually a thing.
yeah, and you estimate things when you don't know the actual certain definite value.
Yeah.
And
like
well,
you
where
don't
would
have
that
the whole
apply?
population. Like when you're testing, say, pHs of Coke.
you don't drink every single cola.
To test that, because then you don't have any Coke to sell. So you take a sample.
You do. And there's a few things about this sample you need to know.
There is.
The size of the sample, n being the number of things in the sample, has to be greater than 30 to really represent anything. If it's less than 30, discard it, it's a rubbish one.
Bad sample.
For example, if I asked, who likes Triv's shirt? If I asked Triv, he'd probably say, yes, I like that. If I asked him, he doesn't seem to like shirts.
No.
Or clothes.
Clothes at all, but he likes that dog.
I don't think the dog likes him.
No, neither. Also, if you asked Wayne about hairdryers, he'd probably say he liked all the hairdryers, because he doesn't got very much hair.
Yeah, I don't know how good they are, it just feels nice on the head. They'll feel the same to me.
There you go. So.
Big sample sizes.
Yep.
And then you do stuff to this sample, find out the results, and then use that as estimating for the population.
You do, you sort of say, because it's like this for the sample, everything else will roughly be the same. So that becomes, everything becomes an estimate of the other. For example, X bar. Now we normally talk about the mean as mu, but because we've got a sample, so the whole population, we use X bar, which is said to be an unbiased estimator of mu.
Yes. You've also got an equivalent of the standard deviation, but here it's called the standard error.
You sort of work it out in two stages. You have to work out the standard deviation first, and then it's this equation.
Yes. So that will find out how wrong these things are compared to the population.
Yes, and then you use it in place of the standard deviation in the equation.
Yes. So it's standard deviation over root n, so n should be greater than 30. So it's bringing all the stuff together.
Yeah. And I think you have a question to bring it even more together.
Yes, we have a nice worked example.
Alright.
Are you ready, Triv?
I'm ready.
Right.
It'll quickly with us up.
Okay, I'll find the question. Okay.
Yes.
It's on page 94 from this book, and it's example 1.
Alright.
An entomologist
Entomologist.
wants to know the mean wingspan in millimetres of a large population of moths. The wingspan of the species is known to have a variance, which is sigma squared, so careful that's not the standard deviation. The square root of that would be the standard deviation.
Yeah.
In the population. She measures a sample of 12 moths to find, and finds these have the wingspans of, and then there's a list here, rather than writing
Did
it
it say
out.
the number of the variance?
8.4. Never listens, does he? So, A is estimate the mean wingspan of the population. So you're estimating the population, you're going to get a mean of this sample, and that's going to be your estimate.
So, shall I write up the things when you talk about it?
Okay.
Alright.
So to work out the mean, we'll just have a list of numbers, and it's just the same as what you're familiar with all the way back in chapter 2, chapter 3, about there.
Yeah.
You just do sigma x over n, where sigma x is all of the x values added together, then divided by the total number that there is, as you would for any list. And then this mean of this sample here actually would represent the population, although in this case the n is only 12, so by our rules in an exam this wouldn't be a very good question.
Would not.
But we'll just float with it. Maybe these moths are nearly extinct, so this pretty much does represent population. Who knows?
Right.
Rather than actually adding them together, it's got the answers. So what is the mean if you add them all together and divide by it?
43.25.
There you go. So sigma x over n equals that. You're welcome to check that out, but as long as we've explained what to do.
Yep, and then it says calculate the standard error of an estimate from a sample size of 12.
Well, we know that n's going to be 12, that was the hint in the question. We know the standard deviation
is the square root of that.
that.
So we could put that in.
Yep.
You could say that the square root of 8.4
Gives you the standard deviation
over the square root of 12.
Yes, and that gives you your standard error. That should be relatively small.
Yeah, 0.837.
And that's how you go about answering those sorts of questions.
Yeah, it's quite simple. That's you. So, then in the book they sort of keep talking about that and then use ideas that we used from the last chapter integrated into it.
Yeah.
But we figured you could cope with that. So we're going to go straight to something else that's new, which is called the central limit theorem.
And this is pretty much just stating that the n has to be greater than 30 to represent anything. And then
More or less,
pretty much.
yeah. It just sort of says, only when you're talking about samples, and if n is greater than this number, then you can use it as long as you use the standard error thing.
Yes. That's all it really states.
Yeah.
So in the moth example, n would actually be smaller than 30 to get, because if there's less moths, then less of a sample would represent the population.
So the central limit theorem wouldn't apply.
Yeah, that's right. And that's all it really says, but it sounds horrific.
Does sound really mean.
So no, done with the mean and all of this stuff. You just do the mean in the same way, you do all this in the same way. Let's, what about the variance? Let's get on to that.
Let's do that.
Variance.
But of a sample.
Yeah. So if I give you another sample and you've got to work out the variance, you just use the old formula, right? It's just quite an easy one. It's just that squared, because that's what variance is sigma x squared over n minus the mean squared, right? It's just that.
Sadly not, Wayne.
Oh no.
I know, you can't remember another formula. And they write it in your formula booklet in the most disgusting way physically possible.
It's true.
They write it out
I'm gonna
originally at
write
the top left.
I'm going to write that out here big. So you can see
But
minus x bar and all that squared and all over.
you might not have X bar, and it's really nasty to put numbers in.
Yeah. So they simplify it in the book for you. They don't really explain how they get it. You don't need to know that, but they simplify it in the book.
And you should use that version.
Yes.
So you should use the version which is
This s squared. Remember, this is representing that squared. It's just it's an
except it's an
estimated.
example.
So it's an s equals sigma x squared minus and then sigma x all squared. That's not the same as that.
No.
Over
n all over n minus 1.
And that's in that book, but not in your formula booklet. So you'll have to remember that unless you want to use that.
Which don't. So
I
remember
wouldn't.
that.
I'd remember that.
And yeah, you have to put them into the equation. So some worked examples to do that.
We do. I'll go get it.
Alright.
We could do with writing that up there as a
Alright,
little
I'll write it
reminder.
up there.
So I'll go get it. It's in the book again. So these are, as Triv said, worked examples. And we're on page 103 first. We've got example 5. I'll read you the question while Triv's writing that up and then rubbing everything out. So it's the speed in kilometres per hour of 10 cars entering a village were, and then gives you a list of these different speeds. Calculate unbiased estimators for the mean and the variance of the speed of cars entering this village. So you've got a sample of 10 cars. Unlikely only 10 cars in the world will ever have gone through the village, so you're finding an estimate. So, how do we do this? First is mean, then is variance.
So we just went over mean. So the mean is
the same as what you would normally do with a list of numbers. Sigma x over n.
adding all numbers together, divide by how many there are.
And
this will give us x bar instead of mu, which is
sigma x, if you just want to write out the steps, is 505 and divided by 10, so
Alright.
it's 50.5. 50.5.
sorry.
mean, that's not scary.
No.
Then you've got to use this new formula for the variance.
Which is a bit evil, so I use red to show how evil it is.
Yes.
Yeah. So, part B.
Yep. Sigma x squared equals 25,833.
Alright.
It really is just plonking the numbers into that formula, but you've got to remember it and it's new, so we're doing it anyway.
Yep.
Minus, and then 505 squared at the top, because we've got our sigma x's up here, it's the same thing in this formula. Over n, which is 10, over 9, n minus 1. It's really as simple as that, and it equals 36.7.
So that's not very hard, they're just using the formula we've looked at. But they don't just ask you that.
No,
They integrate it with all the stuff we did before.
Yes, on the normal distribution curve. So we have a question on that.
Oh, let's rubble this off again.
Alright. Now, for the sake of being quicker, we're doing the values that are in the solution as opposed to typing them into our calculator and doing them ourselves. But other than that, we are working our way through it.
Oh, alright.
So, the second one, a bird sanctuary records the weights of 40 adult barn owls. They love weights, ages, lengths, all this sort of stuff. And this one's weights. And then they give you 40 values, but quite friendly in the question. They tell you what sigma x and sigma x squared is.
Oh, sorry.
So, it's first one is calculate an unbiased estimator for the population variance. So, you're going to be using this formula again.
Okay. So,
and it tells you in the question that sigma x squared, in this case sigma w squared, because w is replacing x,
okay.
is 1,715,707.
Is that?
You're going to write it up.
Oh, okay, I could.
Minus, and then it tells you that sigma x, or sigma w in this case, is 8,275.
Yeah.
You divide that by n, which is 40, and divide all of it by 39.
Also, n is greater than the number that's minimum for a population sample. So we can use this and it all will be estimates that are correct.
Yes, we can just apply the central limit theorem. And that answer is 97.9 if you want to put that there.
Alright.
But it's just plonking numbers into the formula. Now it gets tricky, as Triv said, they entwine stuff together. So, ready for part B?
I am.
The sample mean, so that this unbiased estimator, is 207 grams. But an expert claims that the population mean, the actual one, is 210 grams. What is the probability, is the probability, not a percentage, of getting the mean of 207 or less from a sample of 40, given that the population mean is 210 grams?
So, this is using our normal distribution thing again, so we'll draw it up very quickly.
Yeah.
And it's showing that it's less than our mean, which is in the middle.
Yep. So we're going to be looking at a value about here, in fact, all the area less.
We will.
And we're going to do what we normally do. We do the value affiliated minus the mean divided by the standard deviation, except it's standard error, not standard deviation.
Because it's a sample. So
the top line remains the same. We've got 207 minus 210 on the top. And that's the same as when it's not a sample, when it's the population.
yep, and it's over the standard error.
Which we know is the standard deviation over root n. And the standard deviation is the root of this, because this is the variance.
We'll do this quite quickly.
The square root of 97.9 over the square root of 40. And that's what will be under here.
Yep.
Have you got a calculator, Triv? We'll actually do this one as opposed to...
I haven't, it's over there, should I get it?
Get it? So as opposed to just typing it in, we'll actually do the maths here. 97.9 divided by root 40. I did put root for that. Okay. 1.56. And that's what will be on the bottom here, because it'll be standard error in place of standard deviation.
And that gives us an answer of?
Minus 3 divided by 1.56 gives us minus 1.92.
Oh, right. That's
So-
our Z value.
Yes, so if I standardise it up here,
Okay.
we've got our 0, we've got our nice, beautiful ghost.
Yep.
And here we've got minus 1.92, representing what Triv's drew there.
Yep, and then we have the area they want to find out. And it's still a left. That's a nice version.
But it's negative, so if we did the positive version of 1.92, we'd be finding this area, so you do 1 minus the phi of the positive version of that will be equal to the area of the negative version of that.
It will.
So we're going to need our tables.
We are. Got a table over there.
And on the table is the table, that's handy.
It is handy. So, it's on page.
That's not it.
That's not it.
That's not it.
Still not it. It's quite a lot of tables.
There is no text printed on this page. That's lies.
Don't believe you, AQA.
Sorry, I just did that. That bugs me. Does it not bug you? It bugs me. That's not it.
No.
That's not
There's
it.
quite a lot of tables.
That's it.
You might know which one you're looking for. Talks about Z and its normal distribution functions. Makes sense.
And it draws the thing and says to the left. So,
yeah.
1.92, please, Triv.
Alright,
And we're going to do 1 minus whatever Triv reads to me now.
Is 0.97257, if you want all of them.
Yep, please. Alright. And 1 minus that gives us the area of, well, the probability of 0.027.
Alright.
And that's the probability that it'll be less than that.
There you go. That's alright.
So now we know more about barn owls, I think we can go on to a test yourself.
I think we can. Alright. Question time.
Test yourself, page 108, question 1 from this book.
Sorry, there's a mini earthquake hit. It put me off.
Yeah.
Okay. Right. So, question 1 says, a study showed the time, T, minutes, spent by a customer between entering and leaving Feli's department store. She has a mean of 20, with a standard deviation of 6.
Right.
Assume that T was modelled by a normal distribution. Right. Part A, find the value of T exceeded by 20% of the customers.
Alright.
So
this is a population question, because 20% of all the customers has ever been, the entire population of people that have been to Phillies.
or Feli's or the shop, and they bought
So
things.
it's a population question. We did this in our previous video. If you don't know how to do this, you can check that out, but we'll go through it now.
Yep, so we have a percentage. You want a percentage.
First step, convert that to probability.
So 0.2.
Divide by 100. So
Then
we need the table,
we do
and it's over the page.
the second lot of tables.
It gives you the Z value that corresponds to a probability, and is this greater than or less than? I forget the question.
I think you wrote it up, but
Time exceeded. It's
yeah.
greater than. So we do 1 minus this because that will be on the table, and it is that answer, it's not the negative version. So 0.8, what's the Z value corresponding, please, Trev?
0.8416. So that's our Z value. And if you very quickly draw the thing up, it's exceeding. So is it greater than this thing?
So if we're doing the standardised one, our Z is 0.84, because mean will be there.
Yeah, and we want that side, not the left side, which is what we'll get.
Yes.
So
we could put this into our equation to find Z, which is this value we're trying to find out, minus the mean, which is 20, over 6, equals this Z value. So we times that by 6 and then add 20, we're going to get T.
alright.
It's as simple as that, really. So, I'm timesing this by 6 just to clarify, because that's on the bottom, that's what you do. Then you'll have T minus 20 equals whatever that times 6 equals, and you add 20 onto that value.
And that's 25. How many different places do you think it wants?
I would go to 1, just 1.
Then nothing. That's just 25.0.
So not many people are in the shop for more than 25 minutes. So, I wonder what kind of shop it is.
I reckon it's like the wharf.
Yeah.
Yeah.
I don't tend to spend more than 25 minutes in the wharf, because it smells funny.
It smells funny. So, then we have part BI.
Bye.
Write down the standard deviation of the mean time spent in Feli's store by a random sample of 90 customers.
So it's got the word standard deviation, but then the word sample. So you know what it really means is standard error, and we can work that out. We got that up there.
We have. So that is
Standard.
equal to the actual standard deviation, which is 6, over the square root of our population, which is 90.
90. Square root of 90.
Yes.
And what's that, please, Triv?
Alright.
Quite a tricky question because it says standard deviation, then sample. Whenever you see the word sample, it is a sample.
Yes. And it is equal to 0.632.
Right. And the final colour of green for part 2.
I like the colour scheme, it's good. Yeah. Finds the probability that this mean time will exceed 21 minutes.
Oh my god, so this what?
Find the probability that this mean time will exceed 21 minutes.
Greater than 21 minutes.
Yes.
Right. And we'll draw up another one for this
Alright.
question. The actual thing, not the
Yeah, not standardised.
So now our mean is 20, and we're looking, 21's going to be here.
Yep.
And it's exceeding that.
So that's quite a big area. So,
first we need to standardise it and find the z value corresponding to it. That'll be the first step.
so standardise it in 0.
And z will equal 21, which is the thing we're affiliating with,
Yeah.
minus the actual mean over. And it's a sample, isn't it?
It is.
So it's this value rather than the 6 up there.
So I'm going to take that down in calculator.
Yes, so 1 divided by 0.632, please, Triv.
And that is 1.58.
1.58.
And that is on our tables.
However, if we, yes, and that will be about here, to which it will correspond to this area.
Yep.
But if we find the phi of that, it gives us the area to the left. So we actually want to do 1 minus the phi of 1.58
We
to
do.
get the area to the right. 1 minus, okay, could you find me the phi of 1.58 and I'll type it out?
I can. I think you'll write it out, Wayne.
I could be a computer, you don't know me.
0.94295.
Alright, so let's just say 0.06 and just leave it at that.
Alright.
That's about there.
Out there. And
That's that.
that's that. Is
It's
it
from an actual exam paper.
Yep. 2003. Yeah.
Yep, so it could come up like this, and in fact it does nearly every year. They don't miss these sorts of questions.
No. Yeah. And quite mark heavy as well.
They are very mark heavy. It's
Logic
they normally start off with 1 2 mark questions, then advance them, and these sorts of things, including this one, separate people who don't really understand it and are just doing it willy-nilly to those who really can picture and draw it.
Which are people who watch our videos.
So now let's get on to summary.
I think you should, yeah.
Alright. So,
Yeah, that was estimation.
yes, it actually means something as opposed to just don't be a melon.
Yep. It's good to not be a melon as well.
Well, yeah. And
But-
it's all about if you're using a sample and you've got to represent a population because you can't get the whole population.
For whatever reason, so instead of mu, you have x bar.
And that's an unbiased estimator of mu.
And instead of standard deviation, you have the standard error.
It shows you how far off this estimator would be.
Yeah, and that is standard deviation over the square root of n.
Yep, that's right.
Right.
And the mean, well, the x bar in a sample, you do what you normally do to work out a mean. You add up all the figures you have in your sample, providing it's greater than 30 as a general rule of thumb.
Yep. But the standard deviation and variance are different at a sample.
Yes, and there's a horrific formula, s squared, which is the same as the sigma squared,
Yep.
equals sigma bracket x minus x bar close bracket squared over n minus 1.
Yeah, and that's horrible, so you should remember a different one.
Yep, which is the s squared equals sigma x squared minus then sigma x in brackets
Squared over n over n minus 1. So that one's much easier to put numbers into.
Yep, and that's the bit of a change as opposed to how you would normally work out variance with a set of data.
And apart from that, it's all the same. You use the same things, except when you know it's a sample, you don't use standard deviation, you use standard error. And yeah.
You can see with the example we just went through, the test yourself, they like to combine this chapter with the previous chapter.
Yeah, when you don't know something and you have to get the thing, but you use different numbers basically.
And that's estimation.
That is estimation.
That's everything done. We'll see you at the next chapter.
We will, but first,
Little fact for you.
Wayne, what do you call a group of owls?
Is it a hoot? No, it's not a hoot. It's a parliament.
Maybe they should. Maybe they can replace our one.
Maybe they should.
That'd be a
Should
hoot.
You need to take your card back. I'd like a pot noodle, please. You got some sort of deal, haven't you? You put petrol into shopping trolleys for money.
Yeah, and some sticker bars. I think I'll just quickly get it topped up. Let's go.